This screencast is about the multiple linear regression model and fitting the multiple linear regression model. The deterministic part of the multiple linear regression model requires y to be expressed as a linear function of x1, x2 through xk. Beta 0 is the intercept term. Beta 1 is the coefficient of x1, beta 2 the coefficient of x2, through beta k the coefficient of xk. The deterministic part of the model is also referred to as the true regression equation. The probabilistic part of the model involves the random error epsilon. The random error is assumed to satisfy the INE model assumptions. This U-try asks you to interpret each coefficient and indicate what sign you expect each coefficient to have. You should do this for each row. For example, the first row refers to a multiple linear regression model to estimate the monthly production cost associated with producing x1 units of product 1 and x2 units of product 2. After reflecting on this model, you should decide that the intercept beta 0 would be the monthly fixed cost, beta 1 would be the unit variable cost for product 1, and beta 2 would be the unit variable cost for product 2. All of the coefficients would be expected to be positive. You should work through the remaining 4 examples in this table. You can pull down the text box to check your answers. Interpreting the multiple linear regression coefficients. For any j between 1 and k, beta j can be viewed as the coefficient of xj, or as the increase in y per unit increase in xj, holding the other independent variables constant, or as the slope of y with respect to xj, holding the other independent variables constant, or as the derivative of y with respect to xj. Beta naught can be viewed as the y-intercept equal to the value of y when all of the x variables are 0. Occasionally, beta naught may have no meaningful interpretation in a specific example. Now that we've discussed the multiple linear regression model, we'll describe the estimated multiple linear regression model. The task involves obtaining the estimated multiple linear regression equation y hat equals b0 plus b1 x1 plus b2 x2 plus etc. out to bk xk that best fits a given data set using the method of least squares. Here is, in a general context, what a multiple linear regression data set would look like. For the first data point, x11 is the value of the first variable for the first data point, x21 is the value of the second variable for the first data point, all the way through xk1, the value of the kth independent variable for the first data point. And this is the value of the dependent variable for the first data point, y1. Here are the values for the second data point, all the way down through the values for the last, the nth data point. Of course, in a specific situation, The data would have actual numerical values for x1, x2 through xk and for y. Here are three definitions that are essentially the same as those in simple linear regression. The ith fitted value, yi hat, is the estimate of the dependent variable obtained using the x values of the ith data point. The ith residual value, ei, reports the error when the ith fitted value is used to estimate the y value of the ith data point. Note that when the ith fitted value overestimates yi, the residual value is negative. When the ith fitted value underestimates yi, the ith residual value is positive. The sum of squared error, SSE, is the sum of squared residual values. As in simple linear regression, SSE measures the amount of variation left unexplained after introducing the x variables and the estimated multiple linear regression equation. I've moved to the next page. The derivation of the estimated multiple linear regression equation uses the least square method. The least square method uses calculus to identify the values of b0, b1, b2, all the way through bk that result in the multiple linear regression equation with the smallest SSE value. That is, with the least amount of unexplained variation. The calculus details of the derivation are optional reading and will not be tested. However, two items that appear in the derivation are worth observing. The first is that the residual values always sum to 0. The second is that the sum of all fitted values is the same as the sum of all actual yi data values. The derived expressions for b0, b1, b2, all the way through bk appear in many textbooks and involve matrix multiplications. For multiple linear regression in Business 605, we'll allow Excel's 2-pack to complete these calculations for us. Here are a few comments to complete the introduction to the fitted model. Obtaining a point estimate of a y value given specific values of the xi's remains straightforward. Simply plug the given xi values into the multiple linear regression equation and compute the estimate y hat. To obtain a 100 1 minus alpha % confidence interval for the mean value of many y's, all at the same values of x1, x2 through xk, involves complex computations that, for some reason, Excel 2-pack has not been programmed to do. This same comment applies regarding a 100 1 minus alpha % prediction interval for an individual value of y for specific values of x1, x2 through xk. When these important intervals are needed, they will be supplied by the instructor. The above comments regarding intervals for y values should not be confused with confidence intervals for the beta j. The 95% intervals are always available on Excel output, and other than 95% intervals can easily be constructed using Excel output and a t-table. More on these confidence intervals in section 14.4. This completes this screencast.